It's November 8th, 2025. The solar readings have finally settled. For nearly a week, observatories worldwide have been locked on a single anomaly, a pattern that emerged the moment 3I Atlas brushed past the Sun. At a distance of 1.36 astronomical units, it should have behaved like any other comet, boiling, fragmenting, scattering dust. But instead, the instruments picked up something else entirely. A sudden, localized shift. Not a disintegration, not a flare. A brief, precise alteration in movement and brightness, impossible to explain by heat or radiation alone. This wasn't a glitch. For almost 3 weeks, 3I Atlas followed a flawlessly predictable orbit, unbothered by the uneven jets of gas expected from its icy surface. Then, around perihelion on October 29th, that perfection collapsed. Telescopes from Chile to Hawaii saw it happen, a distinct change in course, followed by a violent surge in light, and then silence. For the first time since Oumuamua, global datasets stopped agreeing. NASA's JPL recorded a faint acceleration away from the Sun. ESA's solar orbiter reported a sudden drop in dust activity, and the Very Large Telescope caught something stranger, a spectral distortion that doesn't match reflected sunlight at all. It's almost as if 3I Atlas reacted to the Sun, instead of merely surviving it. But the real mystery isn't what the Sun did to it, it's what it did near the Sun that no one was ready for. And that's where this story begins. On October 29th, 2025, 3I Atlas reached its perihelion, the moment it drew closest to the Sun. During this passage, the interstellar visitor was exposed to more than 700 watts of solar energy per square meter, an intensity strong enough to vaporize volatile materials from any comet-like body. Astronomers worldwide expected to witness a flare-up, or even a partial breakup event. Yet what unfolded was not chaos, but precision. As it approached the Sun, 3I Atlas held its trajectory with a steadiness that defied natural behavior. For several days, as it neared perihelion, its path remained unwavering. The Solar and Heliospheric Observatory, SESO, tracked it continuously, watching as it skimmed the edge of the Sun's active zone. No deviation, no erratic jets, none of the typical perturbations caused by uneven heating. Every comet previously observed displayed such irregularities when blasted by solar flux, but not this one. Then, suddenly, the readings changed. Within a mere 4 minutes, multiple instruments recorded an abrupt surge in brightness. This was not the gradual increase caused by sublimation. It was instantaneous. For a brief moment, 3I Atlas became almost reflective, its albedo rising to levels that seemed physically impossible for its composition. Some suspected a calibration fault, a software glitch. But 3 independent observatories confirmed the same anomaly. The interstellar object's brightness spiked sharply, then stabilized just as quickly, returning to its original state, as if nothing had occurred. At that very instant, another shift was detected, a non-gravitational acceleration. Hawaii's Pan-STARRS system recorded a subtle deviation in its course, too consistent to be dismissed as noise. The trajectory bent slightly away from its expected path, in a direction almost perfectly aligned away from the Sun. This deviation was coherent, not random, as though the object had responded to something. Those watching the telemetry in real time described the moment as unbelievable. Outgassing, the release of gas jets, could, in theory, cause such accelerations. But the timing made no sense. Natural outgassing peaks hours before or after maximum solar heating, not exactly at it. Moreover, the impulse direction didn't align with the geometry of its tail. If jets were responsible, the object's rotation would have shifted erratically. Yet, no such spin was detected. In the following hours, NASA's Parker Solar Probe, fortuitously aligned for partial observation, picked up an unusual density fluctuation in the solar wind. A compression front passed through the region precisely as 3I Atlas traversed it. The probe's instruments registered an electromagnetic disturbance, faint, but synchronized with the object's position. It was brief, short-lived, narrowly confined, but its timing was too precise to ignore. While coincidence couldn't be ruled out, the sequence of events raised eyebrows among solar physicists. The order was unmistakable. Brightness surge first, electromagnetic fluctuation next, and acceleration last, a progression that implied causation, not random correlation. Astronomers began reanalyzing orbital data immediately. Officially, the Minor Planet Center described the deviation as within plausible limits of non-gravitational effects. But privately, many analysts admitted the truth. No known comet behaves this way. The response of 3I Atlas seemed deliberate, almost intelligent, rather than reactive. At Mount Lemmon Observatory, researchers comparing the light evolution noticed something even more peculiar. The flare-up lacked the spectral fingerprints of dust or gas. There was no trace of carbon or oxygen emissions. No water vapor, nothing typical of cometary activity. The object brightened as though reflecting sunlight, like a mirror, not a comet. Meanwhile, the sun itself was in turmoil. AR 3510, one of the largest active regions of the solar cycle, erupted twice during 3I Atlas's perihelion passage. Both eruptions blasted directly toward the object's quadrant. One coronal mass ejection was powerful enough to disrupt Earth's magnetometers 2 days later. Despite this storm of charged particles, 3I Atlas remained intact and steady. Its structure showed no signs of stress or disintegration. Data from the ESA solar orbiter added another layer of intrigue. Its heliospheric imager captured a faint arc of light accompanying 3I Atlas, not a tail, but an asymmetric halo. When the image was enhanced, analysts spotted a region of localized brightness offset by several hundred kilometers from the main nucleus. Some proposed it could be a detached fragment or a dust plume. Others speculated it might be something else reflecting sunlight independently, a secondary object. But the halo vanished almost instantly once 3I Atlas moved past perihelion. If it were dust, it should have expanded and lingered for hours, even days. Instead, it faded within minutes, as though the reflecting source had simply stopped emitting light. For seasoned comet researchers, this was nearly impossible. Nothing in the known solar system behaves like that. The light curve resembled an artificial flash, instantaneous, focused, and self-limiting. Scientists, hesitant to leap to conclusions, returned to fundamental. During that window, the sun's energy output was abnormally high, nearly double the usual flux for that phase of the cycle. Perhaps 3I Atlas had encountered a strong electromagnetic surge, something beyond our current heliophysical model. If the object's surface were metallic, carbon-rich, or otherwise conductive, such a surge might produce a transient reflective burst. Yet that explanation opened even deeper questions. Conductive surfaces are not typical of natural comet. Neither is a lack of volatiles, or the ability to withstand intense radiation without disintegration. It was as if 3I Atlas were constructed, or composed of materials foreign to our solar system's catalog. That single, unexplainable event near the sun forced astronomers to rethink months of data. From its photometric evolution to its rotation curve, the anomaly wasn't just about what did happen, but what didn't. There was no fragmentation, no gas jets, no thermal delay, only a precise singular change. And in that quiet steadiness, a pattern emerged, one that would dominate every future analysis. Because when 3I Atlas reached its closest point to the sun, it didn't disintegrate. It adapted. That's when scientists realized this interstellar object wasn't following the rules of comets at all. When 3I Atlas was first catalogued as an interstellar object, its motion seemed to fit every known expectation. Its orbit was hyperbolic, confirming it wasn't gravitationally bound to the sun. Its velocity, inclination, and faint light curve all suggested a dormant comet from beyond our solar system. Nothing initially hinted at the defiance of physics that would later unfold. By late October, the global astronomy community had a clear consensus on what would happen during its solar passage. The models were consistent, the predictions logical. None of them were prepared for what came next.
Intense solar heating should have triggered sublimation, the vaporization of surface ices, producing bright jets that drive measurable, non-gravitational thrust. The comet's light curve would normally climb gradually, as these volatiles boiled off, while its spectrum shifted toward the blue as fine dust scattered sunlight. That's the typical dance of a comet under solar fire. That's what Oumuamua failed to do, and that's why astronomers were watching 3I Atlas so closely, to see whether this third interstellar traveler behaved like a comet or like something entirely different. But as streams of data poured in, an unexpected truth began to take shape. The predicted thermal activation never materialized. 3I Atlas displayed weak, inconsistent traces of gas release in the weeks leading up to perihelion, but no large-scale sublimation. Its coma remained faint, almost sterile, as if encased beneath some kind of insulating shell. Even while bathed in direct solar radiation, its thermal output barely fluctuated. At first, this seemed like a small anomaly, a mild mismatch between thermal emissions and brightness. But as the object drew closer to the sun, that minor discrepancy widened into a glaring contradiction. Instead of brightening steadily, 3I Atlas stayed dim. Then, without warning, it fled once, abruptly, before returning to a stable state. It was as though every intermediate stage had been skipped entirely. Researchers at the University of Arizona's Lunar and Planetary Laboratory began modeling this behavior against thousands of entries in cometary databases. The results were confounding. There was no precedent, no analog among the countless comets ever documented. The missing water vapor in its spectrum was especially revealing. A comet this close to the Sun should vent clear signatures of H2O, CO2, and CO, each in predictable ratios. Yet none appeared. If no gas was responsible for its brightness, what was? The simplest explanation was reflection, sunlight glinting off a smooth or metallic surface. But for that to hold true, the object's reflectivity would have needed to increase tenfold within minutes, then drop back to normal. That implies a rapid, coordinated shift in surface geometry, as if a plate rotated, a panel unfolded, or a layer detached in perfect synchronization. No natural comet model could describe that kind of transformation without invoking intentional design. Still, scientists held firm to discipline. Coincidence, not control. Physics, not purpose. Every possible natural explanation had to be tested first, so they turned to the fragmentation theory. Perhaps a surface layer had fractured, briefly exposing fresh ice that boosted its reflectivity. But again, the timing was off. The rotation period of 3I Atlas was too slow for such an event to align exactly with perihelion. And if ice had been revealed, spectrometers would have registered volatile gases afterward. They didn't. Next came the outgassing hypothesis, the traditional explanation for unexplained acceleration. When sublimation occurs unevenly, one hemisphere venting more than the other, it creates thrust like a natural engine. But to produce the acceleration observed in 3I Atlas, the gas output would have needed to be enormous. Such force would leave obvious evidence. Rotational torque, wobble, asymmetry in the coma. None of those effects appeared. For many researchers, that was the breaking point. The instant the data stopped behaving like natural science and started behaving like a signal. Because what 3I Atlas did wasn't random or messy. It was precisely wrong. Its deviations were too clean, too symmetrical. At the European Southern Observatory, analysts tested a new idea, modeling its brightness not as a diffuse dusty emitter, but as a solid reflective body. The fit was much closer. The light curve suggested the object was specular, not isotropic, reflecting light in a concentrated beam rather than scattering it in all directions. In simpler language, it looked shiny. That word, shiny, doesn't exist in the normal vocabulary of comet science, yet it appeared repeatedly in observation logs across independent facilities. One report even noted specular reflection detected, angular phase response inconsistent with porous regolith. The light behaved as if it were bouncing off a dense, compact surface, not a loose dust cloud. The mystery deepened when thermal data was compared. The sunward side of 3I Atlas didn't heat up nearly as much as physics demanded. Under that level of solar exposure, any typical comet would exceed 300 Kelvin, easily. 3I Atlas barely reached half that. Either its surface was radiating heat away with extraordinary efficiency, or something was actively managing its temperature. Thermal regulation in a natural object sounds absurd, yet the math was irrefutable. The emissivity curve hinted at a surface composition unseen in natural samples, possibly carbon-based, but even pure carbon couldn't explain both the albedo jump and the sustained acceleration. One researcher likened it to a solar sail catching light. Another described it as an interstellar echo, a body reacting to solar pressure as though engineered for it. The data kept circling back to the same paradox. 3I Atlas behaved like a comet until the moment it was examined too closely. Then it didn't. It broke every rule of cause and effect. As telescopes tracked its outbound trajectory through early November, the differences between prediction and reality multiplied. Its path remained steady, but consistently offset from all computed model. The unexplained, non-gravitational component persisted, as if the object still felt a force we couldn't see, or continued to generate one. What began as an elegant test of cometary physics had evolved into something far stranger. Fragmentation, gas jets, dust scattering. Each could account for fragments of its behavior, but none explained the sequence as a whole. Quietly, scientists began acknowledging what few dared to voice publicly. We are watching something that follows rules we do not yet comprehend. And yet, amid all that mystery, one fact stood out. Everything, the flare, the acceleration, the shift occurred at the precise moment the sun reached its peak activity in months. A solar maximum delivered one of the most energetic flares of the year. Perhaps then, the answers were not hidden within 3I Atlas at all, but in the star it brushed so close to. Because the next anomaly, the one no one could ignore, came from the sun itself. Every object that passes near the sun feels its gravity's grip, but only a rare few resist it in ways that defy our equations. 3I Atlas was one of them. When its post-perihelion trajectory data was updated, orbital analysts noticed a subtle but undeniable deviation. Small enough to require precision measurement, yet large enough to demand explanation. Initially it seemed like a mundane margin of error, perhaps solar radiation pressure, or slight outgassing, or even calibration noise. But when the same deviation appeared in 3 independent datasets, NASA's JPL, ESA's Solar Orbiter, and the Canada-France-Hawaii telescope, coincidence ceased to be an option. 3I Atlas had changed course, not dramatically, but distinct. Its heliocentric velocity ticked upward by a few meters per second. The new trajectory bent away from its predicted hyperbola by a fraction of a degree, insignificant for a normal comet. But for an interstellar body, hurtling at over 200,000 kilometers per hour, that fraction represented a force that no known physical model could account for. Scientists refer to these occurrences as non-gravitational accelerations, movements that can't be explained by gravity alone. Typically they arise from uneven gas jets that form when frozen material on one side of an object vaporizes, acting like a miniature thruster. But with 3I Atlas, no such activity exists. There are no powerful jets, no broad dust cloud, and no torque induced by spinning. The alteration in its trajectory was smooth, linear, and incredibly precise. When the data is plotted over time, a pattern emerges, one that's far too orderly to be random. The acceleration follows a perfect rhythm, a gradual rise, a brief plateau, then an equally gentle decline. Natural gas vents create chaos, not harmony. This was rhythm. To understand how unnatural that is, imagine firing bursts of gas to push a spacecraft. Each burst leaves behind a jagged signature, intensity and direction fluctuating constantly with rotation, sunlight angles, and surface texture. No natural comet maintains steady thrust without visible instability. Yet 3I Atlas did, sustaining that balance for nearly 8 hours before returning to a stable path. Here's where every model fails. Scientists tried simulating the motion with hypothetical venting regions, variable spin rates, and even unseen mass loss. Nothing fit. The only model that replicated the real-world data was one in which a perfectly smooth surface responds directly to sunlight, as though light itself were pushing it forward. That principle, solar sailing, is a concept from engineering, not astronomy. It describes an ultra-thin reflective sheet that converts photon pressure into motion. Strangely, the acceleration of 3I Atlas matches exactly what a reflective surface, only a few dozen meters wide, would experience at its solar distance. But nothing naturally occurring in the cosmos behaves that way. Back in 2018, when Harvard astrophysicist Avi Loeb proposed that Oumuamua might have been propelled by light pressure, most scientists dismissed the idea. The odds of an interstellar object having the right shape and reflectivity to function like an artificial sail seemed absurd. Yet now, the data from 3I Atlas forces those same equations back into the conversation, because the math fits too perfectly. At around 36 astronomical units, photon pressure alone could explain the acceleration if the object reflected more than 90% of the light that hit and had a thickness under 1 millimeter. Those traits are unthinkable for any natural rock or icy body, but completely normal for engineered materials. Still, most scientists resist such implications. Extraordinary claims demand extraordinary proof, and all evidence so far remains indirect. No telescope has resolved the object's shape. Its brightness curve hints at an elongated form, but that's only speculation. Yet one tangible clue keeps reappearing: the polarization of its reflected light. During perihelion, the European Space Agency's polarimeter detected negative polarization, the same rare phenomenon once recorded in Oumuamua. In simple terms, the reflected light aligned opposite to what's expected from a dusty or icy surface. Negative polarization implies something smooth, dense, possibly metallic. The signal was brief but measurable, disappearing once the object drifted beyond the sun's glare. If that data holds, 3I Atlas becomes only the second known interstellar visitor to show both non-gravitational acceleration and anomalous polarization, the twin signatures of a category we don't yet understand. Even more compelling is the direction of that acceleration. It wasn't random. It pushed almost perfectly outward, directly away from the sun, as if reacting to sunlight itself. When NASA's Jet Propulsion Laboratory recalculated its orbital path, analysts noticed that the deviation aligned with the same region of the sun where a massive solar flare erupted that day. That coronal mass ejection hurled billions of tons of charged plasma, yet 3I Atlas passed just ahead of it, too early for the blast to cause its shift. Unless, somehow, the object reacted not to the material flare, but to its electromagnetic precursor, an invisible surge preceding the plasma wave. That idea borders on speculative physics, yet it's not impossible. Some plasma scientists note that conductive surfaces can experience subtle forces from fluctuating magnetic fields, even without direct contact. If 3I Atlas contained highly conductive materials, metals, or carbon composites, then solar magnetic fluctuations could, in theory, generate currents strong enough to alter its path. But here's the catch. No known comet has ever exhibited this kind of behavior. None possess such structural uniformity or conductivity. Still, the Max Planck Institute team decided to model electromagnetic interactions between a conductive body and a solar field. Their findings were inconclusive, but undeniably intriguing. A body with conductivity similar to nickel could experience an impulse that perfectly matches the measured deflection, and nickel, interestingly, was one of the elements identified in its spectral data. Not impossible for natural objects, but in this concentration, and paired with carbon-rich compounds seen in the infrared, it suggests something else entirely: refined material. Every hypothesis leads to a paradox. If it's natural, it breaks the laws of physics as we know them. If it's artificial, it implies a level of design that originated far beyond our solar system. Most researchers settle on a cautious middle ground, calling it unclassified physics, something we simply don't model yet. But behind closed doors, some admit the pattern feels too intentional. The timing was uncanny. The acceleration began as the sun flared, peaked with the flare's energy front, and faded as the system calmed, like an interaction, not coincidence. Whether that interaction was physical, electromagnetic, or intelligently controlled, no one can yet say. What's certain is this: the deviation was real, measurable, and caused by no known gravitational or mechanical process. 3I Atlas changed its course, not chaotically, not randomly, but in synchrony with the sun's own pulse. And that pulse, when examined in detail, opens another chapter, because the sun that day wasn't calm, it was raging. On October 29th, the sun was in full eruption. As 3I Atlas reached its closest approach, solar activity surged to one of the year's peaks. A sunspot cluster known as AR 3510, twisted with magnetic tension near the equator, released two massive flares in under 24 hours, both directed almost perfectly along the ecliptic plane. Ordinarily, astronomers treat solar flares as background noise when observing near-sun objects. The sun is volatile all the time, but this event was surgical. The first flare erupted within minutes of 3I Atlas's closest pass. The second came 6 hours later, exactly when its trajectory began to shift. NASA's Parker Solar Probe, orbiting just 0.3 AU from the sun, recorded something during that exact window: an intense electromagnetic surge unlike anything it had detected for months. The spike rose sharply, then collapsed, as if something had briefly distorted the solar wind itself. The disturbance was narrow, localized, fleeting, and its coordinates lined up almost perfectly with 3I Atlas's flight path. When solar physicists reviewed the probe's telemetry, they found that the plasma wave signatures didn't match the flare's geometry. The shock wave from that solar eruption should have expanded in all directions, forming a perfectly symmetrical shell of plasma. But it didn't. One narrow corridor of the solar wind displayed an abnormal compression, almost as though it had collided with something unseen. A region of resistance, as if an invisible object had cut through space. There were no spacecraft nearby, no debris, and no known solar process to explain it. Yet again, the timing lined up exactly with 3I Atlas's passage. At that same moment, solar telescopes on Earth captured brief flashes of light near the predicted position of the object, fleeting glints that appeared and vanished in fractions of a second. These weren't sustained reflections, but isolated bursts. Observatories like Mauna Loa and NASA's Solar Dynamics Observatory detected at least 4 of them, spaced at nearly equal time intervals. In raw data, such regularity is impossible to ignore. The first assumption was that these could be instrumental artifacts or stray cosmic rays. But when the same flashes appeared across independent detectors, that explanation fell apart. What scientists saw, in essence, were light pulses that seemed to reflect in rhythm with the solar flare coming from a moving target that should not reflect that way at all. At first glance, it might sound unremarkable. Near the sun, light flickers and noise are common. But astronomy is built on patterns, and this one was structured, each flash aligned with subtle fluctuations in the solar field's intensity, as if 3I Atlas's brightness was modulating with the sun's pulse. Dr. Elena Kov, a plasma physicist at the Space Research Institute in Moscow, proposed an intriguing theory just 2 days ago. In her paper, she suggests that if 3I Atlas's surface contained metallic compounds, then coronal mass ejections could temporarily induce surface currents. Those currents, in turn, might discharge as rapid bursts of light, self-generated flashes, that flicker in sync with the sun's electromagnetic waves. The hypothesis is fascinating, but relies on a major assumption that 3I Atlas conducts electricity as efficiently as engineered alloys. Natural metallic meteorites can conduct to some degree, but not with that kind of precision, and certainly not in perfect rhythmic intervals. To understand how bizarre this is, compare it to what happens to a normal comet near perihelion. Its surface heats unevenly, ice turns to vapor, dust erupts chaotically, and the nucleus tumbles unpredictably. Radiation tears it apart in bursts of disordered energy. There's no rhythm, only chaos. 3I Atlas, in contrast, behaved like it was synchronized with the sun. The flare's energy rose, it brightened. The flare faded, it dimmed. The time lag between cause and effect, just seconds, not hours. Far too fast for any natural thermal reaction. Some scientists likened it to a mirror flicking sunlight. But mirrors don't flick themselves. Others proposed it might be an optical illusion, perhaps caused by the sun's turbulent plasma refracting light in complex ways. But computer simulations failed to reproduce either the pattern or frequency of the flashes. The only model that matched reality required the reflecting surface to shift its orientation intentionally, as if something was controlling it. Intentionally, a word that doesn't belong in astrophysics, yet it keeps resurfacing whenever 3I Atlas is discussed. As more data arrived, the idea of coincidence began to fade. The object's behavior resembled coupling, a kind of interaction between it and the sun. Whether that exchange was electromagnetic, optical, or something beyond our current understanding, it was clear this was interaction, not passive exposure. In the hours after the event, radio telescopes scanning near solar space detected transient bursts in the megahertz range, short-lived emissions lasting less than a second. They came from the exact region where 3I Atlas had been tracked by the solar orbiter. The signals weren't strong enough to establish a clear source, but their spectral shape didn't fit any known solar background noise. Officially, scientists called it plasma interference. Unofficially, the coincidences were becoming impossible to ignore. A solar flare, precisely timed light pulses, a measurable shift in trajectory, localized magnetic turbulence, all within 10 hours. For reference, when comet Lovejoy approached the sun in 2011, it disintegrated completely. Its nucleus couldn't endure the radiation. Yet under nearly identical conditions, 3I Atlas did the opposite. It stabilized, adjusted its course, and emitted structured reflections. The following day, as the sun quieted, so did 3I Atlas. The solar orbiter's readings normalized. The Parker probe detected no further disturbances. Brightness fell back to baseline, and the non-gravitational acceleration leveled off. Whatever had happened, it was finished. And yet, the implications refused to fade. This wasn't a single anomaly. It was a sequence. The flare, the shift, the flashes, the silence, each perfectly timed, each echoing the sun's rhythm. When astrophysicists synchronized every available dataset, solar, optical, and radio, The results were unnerving. Every measurable irregularity in 3I Atlas's motion corresponded exactly to fluctuations in the sun's electromagnetic field. In other words, the object responded to the sun as if it understood it. That conclusion doesn't appear in official paper. The tone in those publications is cautious, deliberately neutral. But between the lines, unease is unmistakable. 3I Atlas didn't just survive perihelion, it participated in it. And as it drifted outward again, another enigma surfaced, one that shattered even the most conservative natural explanations. Because if light and heat couldn't explain its behavior, perhaps the answer lay in its composition. That's where the next chapter begins. The thermal inconsistencies. Infrared data from both Hawaii's Infrared Telescope Facility and the ESA Solar Orbiter's infrared suite revealed something so unexpected that analysts initially thought the instruments were miscalibrated. The object's surface temperature, even at peak solar exposure, was dramatically lower than any comet or asteroid ever measured at a similar distance. At 1.36 astronomical units, the expected equilibrium temperature for a dark body should be about, for a highly reflective one, maybe 240 Kelvin. But 3I Atlas never exceeded 170 Kelvin. That's not random noise. It's a direct violation of known energy balance. Either it was absorbing less sunlight than physics allows, or it was emitting energy in a way we don't yet understand. Typically, cooler temperatures imply high reflectivity, a surface bouncing light rather than absorbing it. But the spectral data contradicted that. 3I Atlas's visible spectrum wasn't that of a pure mirror. It displayed muted absorption bands, suggesting its surface was interacting with light selectively. In simpler terms, it was reflecting some wavelengths, while trapping others, as though tuned to specific frequencies. This selective behavior baffled thermal physicists. No known mixture of silicates, ices, or carbon compounds can behave like a wavelength filter, yet that's precisely what the data showed. Some frequencies bounced off efficiently, while others vanished entirely from the emission spectrum, absorbed, transformed, or hid. The first hypothesis was that dust might be concealing the signal, a cloud dispersing the infrared spectrum, but high-resolution imagery from the solar orbiter quickly ruled that out. The region surrounding the object appeared pristine, free from the dense, hazy envelope typically seen around dust-cloaked comets. That left scientists with very few possible explanations, and none that fit neatly within established physics. When researchers reconstructed the object's thermal evolution minute by minute, an unsettling pattern appeared. Its temperature didn't climb in a smooth, predictable curve as it approached the sun. Instead, it flickered, small, rhythmic oscillations every 20 to 30 minutes, like a faint heartbeat. Each of those pulses perfectly coincided with micro-fluctuations in the solar wind's magnetic field. The variations were far too weak to disturb any ordinary celestial body, yet the synchronization was flawless. It was as though 3I Atlas was reacting to environmental shifts faster than natural physics should allow. Normally, a comet's dusty, icy surface absorbs energy slowly and releases it over time. The lag between heating and cooling spans hours. But 3I Atlas responded in seconds. Something on or beneath its surface was adapting instantly, either dispersing heat with unmatched precision or actively controlling its temperature. One theory floated within the scientific community was endothermic sublimation, a process where certain volatile compounds absorb heat as they change phase, effectively cooling the surface. Yet no corresponding gas release appeared in the data. There was no venting, no trace of expelled material in the surrounding plasma. If a chemical mechanism was at play, it left no detectable signature whatsoever. Attention soon turned to the object's thermal inertia, or rather its absence. Observations from multiple spacecraft revealed that as sunlight shifted across its surface, the warm zone followed the illumination perfectly, as though tracking it in real time. This implied an instantaneous redistribution of heat, almost mirror-like in behavior. Natural regolith doesn't act that way. Even metallic meteorites show delays as heat diffuses through their structure. 3I Atlas showed none. When researchers simulated this phenomenon, only one class of materials displayed similar properties: ultra-thin conductive composites, capable of spreading thermal energy across large surfaces almost instantly. In engineering terms, this would resemble a heat management system, or something strikingly similar to one. In fact, one early unpublished paper submitted to the Astrophysical Journal briefly used the term radiative control surface to describe the effect before revising it to non-uniform thermophysical properties. The meaning, however, remained clear. The surface behaved as if intentionally engineered to withstand and regulate heating. What deepened the puzzle was its durability. Objects with such high reflectivity usually lack structural integrity, fragile, prone to disintegration under extreme thermal stress. Yet 3I Atlas endured one of the most intense solar encounters of this cycle, without releasing a single detectable fragment. Its resilience defied every thermal and mechanical expectation. NASA's infrared spectrograph team suggested another idea. Perhaps the object was coated in refractory minerals like corundum or spinel, substances capable of surviving at scorching temperatures. But these minerals produce unmistakable spectral fingerprints, none of which appeared in the readings. Others speculated it could be encased in a carbon-rich shell, perhaps similar to soot hardened by cosmic radiation. Yet soot tends to darken under intense light, while the data showed the opposite. The object's albedo increased as it was illuminated. By this stage, quiet speculation rippled through the scientific community. Some theorists dared to draw parallels to artificial structures, relics or constructs designed for self-protection in extreme conditions. Publicly, however, the tone remained cautious. Phrases like reflectivity modulation began replacing the bolder adaptive surface. Still, every publication, regardless of its restraint, gravitated toward the same unspoken implication. The thermal behavior appeared deliberate, purposeful. Then came another revelation. Unlike typical celestial bodies which emit infrared radiation evenly in all directions, 3I Atlas radiated asymmetrically. Its heat signature favored the side facing away from the sun, suggesting that absorbed energy was being redirected and expelled directionally. That's something even modern spacecraft struggle to achieve. A researcher at the National Astronomical Observatory of Japan studying high-speed photometric data from the Subaru telescope noticed an unprecedented event, a polarization reversal during one of the brightness surges. The direction of polarized light flipped by 80 degrees, something never documented in any comet or asteroid. It indicated not random scattering, but a coordinated realignment in the way the surface interacted with sunlight, almost as though it reconfigured its optical properties in real time. Such behavior has only ever been observed in engineered materials, specifically in liquid crystal arrays, metamaterials, and polarized reflective surfaces that can modulate incoming light. For a naturally formed interstellar fragment to display this kind of control seemed impossible. Yet the data fit perfectly. Further analysis of the flare's spectral data revealed subtle irregularities. When scientists subtracted the solar background, faint peaks emerged at 10.8 and 11.3 micrometers wavelength, characteristic of nickel-carbonyl compound. Remarkably, those same peaks had been faintly present earlier in the object's inbound trajectory. Nickel-carbonyl is highly unstable in sunlight. It breaks down rapidly, releasing metallic nickel vapor capable of reflecting light intensely. But for that breakdown to occur exactly at perihelion, during the peak of solar radiation, would require impeccable timing, not coincidence. That means the compound had to be somehow shielded, then exposed precisely when the sun's energy reached its maximum. Nature doesn't time things that perfectly. The uniformity of the subsequent brightness surge was equally astonishing. High-resolution imagery from the Very Large Telescope showed no uneven coma, no trailing jets, no hotspot. The entire surface brightened simultaneously, as if the object itself became a light source. In natural bodies, illumination varies with surface orientation. Regions turned away from the sun remain dim. Yet 3I Atlas glowed isotropically, as though light emanated from within rather than bouncing off it. To explain this, astrophysicist Luca Ferraro from Bologna proposed an extraordinary hypothesis: internal luminescence. He suggested the object might contain embedded crystalline lattices, capable of fluorescing under intense radiation, much like phosphorus or advanced carbon nanotube structures. When struck by high-energy solar particles, these lattices could emit light briefly, producing a glow not of reflection, but of re-emission. The idea bordered on science fiction. No known natural interstellar material has ever shown such properties, yet the light curve fit Ferraro's equations perfectly. The data revealed an exponential decay consistent with radiative recombination, not thermal fading. If correct, it means 3I Atlas wasn't reflecting sunlight at all. It was emitting it. That single revelation, if verified, could rewrite the fundamentals of planetary science. An object that glows only under specific conditions, synchronized with solar energy, behaving not as inert rock, but as a passive energy converter. For the next 72 hours, astronomers watched in stunned disbelief. The light curve flattened again, its brightness stabilizing as though nothing had ever happened. The mysterious object resumed its steady trajectory, unaltered in spin, orbit, or velocity. It was as if the flare, the extraordinary outburst that had mesmerized the scientific community, had never occurred at all.
In closed discussions, a few theorists began referring to it as a controlled reaction, while others, wary of the implications, preferred the phrase coherent optical anomaly. Whichever term they used, one thing was beyond dispute. This event was not random. It didn't behave like a natural cometary flare or a thermal outburst. The precision of its timing and decay suggested a response, not an accident. A deliberate reaction to heat, radiation, or an external stimulus we still don't understand. An internal memo circulated within the International Union's Interstellar Object Working Group captured the moment's unease. One line stood out starkly. If such behavior were seen in an artificial satellite, we would describe it as a calibration test. The unsettling part, of course, was that this object wasn't a satellite. It wasn't even bound to our sun. The flare had done more than alter the light. It had altered the conversation. For the first time, even the most conservative scientists began to whisper the possibility that 3I Atlas might represent a class of interstellar objects never before observed, entities capable of reacting dynamically to stellar condition, not merely through chemical or physical change, but in a manner that implied adaptation. Whatever the cause, one conclusion became inevitable. If the brightness spike was real, it had to leave spectral fingerprints. So the world's telescopes turned back toward the traveler, hunting for clues in the frequencies of its light. When the surge faded, the spectrum didn't revert to normal. At first, the shift was subtle, barely perceptible changes in hue. But over the next 24 hours, the light from 3I Atlas began to transform in ways that defied every conventional model. Normally, after such an outburst, a comet's spectrum would settle back into its baseline, characterized by dust scattering, faint molecular emissions, and weak sunlight reflection. This one did. Instead, it displayed razor-sharp, narrow emission lines, features that no comet or asteroid had ever shown. The first team to notice the anomaly operated the Very Large Telescope in Chile. Using the X-shooter spectrograph, they detected faint emission peaks near 470 and 520 nanometers, wavelength where neither water, carbon dioxide, nor hydroxyl radicals emit light. The lines were narrow, coherent, and most puzzlingly stable. They persisted for hours before fading away. In spectroscopy, such sharpness is often the hallmark of engineered resonance, not natural radiance. But what truly startled the community wasn't the lines themselves, it was their mathematical spacing. When analyzed numerically, the distance between the peaks corresponded exactly to a 1:2 ratio, a geometric constant, not a chemical one. Nature doesn't produce that. Spectral lines arise from quantum energy transitions, unique to specific molecules, not from mathematical harmony. Skeptics first dismissed it as an optical artifact, scattered sunlight or interference within the detectors. But that theory unraveled quickly. Independent observations from Ka, Subaru, and La Palma all recorded the same precise spacing, using different instruments, under different atmospheric conditions, and from different hemispheres. Yet every dataset showed the same rhythmic pattern. It was as though the light itself carried encoded information. The most conservative explanation proposed was interference, sunlight reflecting from a surface with microstructured layers, or ridges that diffracted the light in predictable intervals. But to produce that kind of structured signal, the surface of 3I Atlas would require submicron precision over kilometer scales, a degree of organization consistent with engineering, not random geology. To test this, researchers ran simulations of how light would behave when scattered off layered composites, thin carbon laminates, crystalline lattices, ultra-smooth films. The results were chillingly accurate. Structure composed of nanometer-thin repeating layers could indeed generate identical spectral spacing through constructive interference. In simpler terms, 3I Atlas might be layered. The implications were staggering. Layering requires precise cycles of deposition, heating, and cooling processes that cannot spontaneously occur in the empty vacuum between stars. Yet, the data refused to align with any simpler model. Infrared spectrometry added more between 10 and 12 micrometers. Two faint absorption bands appeared that matched no known mineral compounds.
Their wavelength roughly corresponded to nickel tetracarbonyl and other complex organometallic molecules, substances that can only form under controlled chemical conditions. On Earth, nickel tetracarbonyl is used in industrial metallurgy, specifically in refining and purifying metals. It's also volatile and decomposes under sunlight, which meant that if those molecules truly existed on the object, they must somehow be replenished or shielded. That conclusion was too extraordinary to announce outright, so official papers mentioned it indirectly, using cautious phrasing like transient metallic carbonyl features. But everyone understood what that really implied. This wasn't ordinary cosmic debris. As if that weren't enough, 3I Atlas's reflectance spectrum flattened in a completely unnatural way. Instead of sloping toward the red end, typical for dusty, uneven surfaces, it became achromatic, reflecting all visible wavelengths, nearly equal. That's a signature often seen in engineered alloys or coated composites designed to maintain neutral color across light spectrums. A research group at Harvard took the investigation further, correlating polarization data with brightness measurements. What they found stunned them. The phase angle dependence, the way brightness changes with viewing angle, was virtually zero. Natural comets show steep rises because dust scatters light unevenly. 3I Atlas, on the other hand, reflected light uniformly, like a Lambian reflector, the theoretical model of perfect reflection. In nature, nothing behaves that way. Only artificial materials, such as spacecraft panels, even come close. By this stage, the community had abandoned the word comet. Official documents labeled it an interstellar object. But in private communications, new terms emerged: structure, artifact, reflector. Words chosen carefully, but each hinting toward a single uncomfortable idea. Some physicists tried to salvage a natural explanation by invoking fractal carbon networks, hypothetical materials formed in interstellar space, where carbon atoms might assemble into complex lattice geometries. Theoretically, such materials could generate strange optical signature, but the temperature data demolished that theory. Those fragile networks wouldn't survive perihelion. They'd vaporize long before generating coherent light patterns. Yet 3I Atlas passed close to the sun and remained intact, pristine, and unscathed. Then came one final revelation from the Hubble Space Telescope. Despite the blinding interference of solar radiation, its ultraviolet detectors recorded faint absorption features near 280 nanometers, corresponding to magnesium oxide, a compound known for exceptional heat resistance and reflectivity. The presence of magnesium oxide, alongside nickel and carbonyl compounds, suggested one of two impossible truths. Either the object formed in an environment far more chemically diverse than any known star system, or it was a composite, assembled from refined, processed material. Weeks later, the data remains irreconcilable. No single natural model can account for every spectral feature. Each line contradicts another. If the object is metallic, it shouldn't contain volatiles. And yet it does.
For researchers, this moment was unsettling. The more they analyzed the data, the more 3I Atlas defied every natural rule in the book. If the surface truly contained carbon-based compounds, it shouldn't have reflected blue wavelengths so efficiently. If it was composed of layered materials, it shouldn't have survived the full brunt of solar radiation so close to the sun. But the real shock wasn't in what its spectrum revealed. It was in what it concealed. Hydrogen, the simplest, most abundant element in the universe, was missing. Every known comet, asteroid, or interstellar fragment, regardless of its age or origin, carries traces of hydrogen compounds, water, hydrocarbons, or ammonia. Yet 3I Atlas showed none. Its spectrum was barren, devoid of the faintest hydrogen signature that defines nearly every natural celestial object. This absence, subtle but absolute, quickly became the most incriminating piece of evidence yet. Without hydrogen, it couldn't be a comet. Without volatile compounds, it couldn't account for its motion or its surface activity. Without absorption features, it couldn't justify its thermal stability. What remained was an object that behaved less like an astronomical body and more like a mechanism, or perhaps the remnant of one. Many in the scientific community rejected that conclusion outright. And so, investigations continued.
deeper, more desperate. Researchers proposed everything from unobserved photochemical interactions to exotic crystalline coatings that could mimic metallic reflectivity. Others speculated about rare ice polymorphs, forming under interstellar radiation pressure, that might somehow imitate engineered materials. But as the datasets accumulated, natural explanations began to crumble. What emerged instead was a repeating pattern, consistent, deliberate, and undeniably structured. That brightness flare, the one that had shaken the astronomical world, no longer appeared random. It now seemed like a deliberate response, a shift in how 3I Atlas interacted with sunlight itself. Before perihelion, it behaved like a lifeless rock. Afterward, it transformed into an active reflector, responding to radiation as though guided by design. And this transformation wasn't limited to light alone. It began to reshape something far more tangible, the very feature that defines every comet ever observed, its tail. What followed next would overturn centuries of astrophysical understanding. It came to be known as the dust tail mystery. When 3I Atlas re-emerged from the glare of the sun, telescopes across the world prepared for a familiar sight, the elegant arc of a comet's dust tail, curving gracefully away from the star, carried outward by solar radiation and wind. But the images that arrived shattered that expectation. At first glance, the object's tail looked ordinary, a delicate stream of dust trailing behind it, faint but visible. Then within mere hours, high-resolution imaging exposed something no one had ever seen before. The tail wasn't flowing away from the sun, it was bending toward it. Confusion spread instantly. Data was rechecked, orientation models recalibrated, instruments revalidated. Some thought it must be an illusion, a quirk of overlapping coronal streams, or solar background noise. But as new data poured in from observatories across the world, the impossible persisted. Spacecraft from entirely different vantage points confirmed the same geometry. The tail of 3I Atlas pointed upstream, directly against the flow of solar wind. Though rare anomalies had been recorded before, none were remotely similar. In 2010, comet CA 2021-2A2 displayed an odd, fractured pattern, later explained by a violent collision. But those debris clouds were chaotic, asymmetrical, fragments scattered without order. The tail of 3I Atlas was the opposite, smooth, stable, and uniform, as if held taut by unseen forces. To understand why that was impossible, scientists revisited the basic physics of cometary behavior. Ordinarily, sunlight and charged solar particles push dust outward from the comet's core. Larger grains drift slowly, smaller ones are swept away faster, forming a predictable fan-shaped trail. Gravity, gas emissions, and radiation pressure sculpt this pattern, but the direction always remains the same, away from the sun. 3I Atlas broke that rule. Its dust didn't disperse, it converged. The particles gathered inward, forming a narrow, faint plume that seemed to move with the object itself, rather than behind it. Light scattering analysis soon revealed an even stranger trend. The dust wasn't drifting freely through space, it was accelerating alongside the nucleus, synchronized in velocity, almost as if trapped within a magnetic current. That discovery redirected attention toward one possibility: electromagnetism. Could 3I Atlas carry an electric or magnetic charge powerful enough to deflect solar wind? In theory, yes, but only if it possessed field strengths thousands of times greater than any natural body its size could possibly generate. No known comet or asteroid had ever exhibited such magnetic behavior. NASA's Heliospheric Imaging Division ran simulations, feeding in charged dust parameters and solar field data. The results were astonishing. Only a body encased in a near-continuous magnetic envelope, essentially a magnetized shell, could reverse dust flow so coherently. And a magnetized shell implied one thing: metallic conductivity. That in turn tied directly back to earlier spectral readings. Nickel traces, magnesium, carbonyl signatures. Suddenly all those scattered anomalies began to align into one unnerving picture. But then came another surprise, captured by the solar orbiter's remote imaging system. Around the inverted dust tail, a faint crescent appeared, glowing ahead of the object rather than behind. Sunlight seemed to scatter around it in a way eerily similar to a bow shock, a plasma deflection pattern, seen not around comets, but around spacecraft. In other words, the solar wind wasn't striking 3I Atlas directly, it was bending around it as if encountering a magnetic barrier. Data from the Parker Solar Probe later confirmed this. As the object moved away from the Sun, sensors recorded a subtle but distinct drop in particle density, trailing behind it, a void several thousand kilometers across. This meant the solar wind had been diverted, exactly the way it behaves around planets, with magnetic fields or artificial plasma shields. The implications were staggering. For an object barely 100 meters across to generate such an effect, it would need to either actively respond to the Sun's magnetic field, or produce one of its own. Both scenarios lay far beyond the limits of natural astrophysics. Even more unsettling were the details that emerged in enhanced imagery. The reversed tail wasn't a simple plume, it was structured. Within it, faint filaments appeared, evenly spaced strands that pulsed softly in brightness. Each pulse matched solar fluctuations, at roughly 90-second intervals, the same rhythm as alpha waves propagating through magnetic plasma fields. 3I Atlas didn't just withstand those waves, it seemed to channel them. Some heliophysicists began to whisper the unthinkable, that the object's metallic layers could be inducing currents as it moved through charged space, creating a self-sustaining magnetic dipole. If true, this meant 3I Atlas wasn't merely reflecting sunlight, it was reacting to it. Yet even that failed to explain the precision. For nearly 12 continuous hours, its tail maintained flawless symmetry, perfectly aligned despite turbulent solar winds, before abruptly dissolving into silence. Natural dust never behaves that way. It disperses chaotically within minutes. Whatever was holding that structure together, held it deliberately, then released it all at once. And when all the data was overlaid from multiple instruments, one haunting realization surfaced, one that would change everything.